So the title of my talk is The Physics of Thought and the Architecture of Intelligence. Before going into that, though, I thought I'd actually start with a little bit of reflection on NSDI. Hakeem did a great job, but in 2002, roughly, what Tom Anderson and I observed, and I was early in my career at the time, and really excited about the systems community, operating systems community. That's where I grew up. I was getting more and more interested in the networking community, SITCOM. I noted at the time in reading the SITCOM papers that most of them didn't have a real evaluation section. So they were these great papers, great ideas, but it was hard to tell whether or not they worked. Operating systems community, in my opinion, I was biased, of course, set the standard for how performance evaluations, systems evaluations would happen. And so what I thought is we needed a community that could act as a bridge, right? And the future, right around 2002, 2003, was about networked systems. Of course, including operating systems, but distributed systems, networking, even databases. So we kicked off the conference with actually generous support from USENIX. I can tell the story about the skepticism that many had about starting a new conference at the time. I'm glad that we got the support from USENIX to make it happen. And wow, has this community come a long way, right? And you saw the statistics, 120 submissions versus 700, more than 100 accepted papers, 7x the PC size, still really a very selective conference, 22% acceptance rate. We've now gone to multi-track, et cetera. It really has gone stood the test of time in also managing the shifts in the community, right? So in the early days, 2004, it was the internet scale era. DHTs were popular. Peer-to-peer systems were very popular. WAN, of course, was hugely popular. Next decade was about the data center era, right? Topologies, RDMA, software-defined networking, and of course, cloud. And what we're seeing over the past 6 years is it's the AI and ML era, systems for ML, ML for systems. NSDI has kept more than pace. It's actually led these transitions in research. One of the things that I'm also most proud of is that, frankly, when NSDI started, it was probably a US, maybe a little bit of Europe-centric conference. Today, it's truly global. And I think that's reflected in the set of papers, authors, and more. And that's fantastic to see. So what continues to remain is, I think, the spirit of the community. Right? The NSDI philosophy of build it, measure it, prove it, remains the same. I think this community sets the standard today in terms of what it means to actually carry out the deepest, most meaningful evaluations of the most complex systems. I mean, in other words, just figuring out how you evaluate your ideas in systems in NSDI is a real challenge. Doing it well, doing it convincingly is a real challenge. And that's reflected in the selectivity of this conference. It's reflected in the great work that you're doing. I think that people come out of the NSDI community really well prepared for the future. That's probably one reason why so many people submit, I guess, 10 plus papers, et cetera, as well. That was surprising to see. But I also want to stress that people really read the NSDI proceedings in industry. And so to the extent that a big part of research is about having impact with your work, I can tell you for certain that the ideas that maybe first started as wild and crazy at NSDI now underlie many, many hyperscalers infrastructure. Yes, Google, but Amazon, Alibaba, Azure, you pick. Okay, and that I think is the ultimate test of a truly impactful community. So you should all have a lot to be proud of as well here. Okay, so with that background, we'll go to the talk. It is, it goes without saying, one of the most exciting times to be doing research, one of the most exciting times, probably the most exciting time ever, to be doing research and development in network systems. It feels disruptive, right? And many of you, I think, are feeling the disruption, or feeling maybe even a little bit of anxiety around what this moment means for the future of research, for the future of development, maybe even for the future of technology and society. I think about this a lot. For me, one of the biggest guides is to actually look back on history. So I'm going to start with some non-traditional computer science material and go back several hundred years in history to try to draw some parallels for us to reason about what we're going through today. And then I'll transition to what this means today as AI transforms our world, and how that then translates to what I call the architecture of intelligence. We'll talk about hardware, we'll talk about networking, of course, and we'll talk about compute. And then we'll wrap up with what lies ahead in front of us. Okay, so what I want us to think about here is that this moment does feel very, very disruptive, but it is the latest of what has been a series of very, very disruptive moments in history, and that they're coming faster and faster, right? I lay out some of them here. The Renaissance, right, starting about the 1300s, the scientific revolution, the Age of Enlightenment, the first industrial revolution, right, steam, the second industrial revolution, internal combustion, electricity, the atomic space age, of course, the information age, which we're in and coming out of, and now this era of intelligence. I'm going to zoom in on one, the Industrial Revolution. And I'll highlight one particular invention that maybe, there's lots of debate here, but I'm going to pick one that probably set it off, and that was Thomas Newcomen inventing the atmospheric steam engine. Right, the idea here is that you could heat up water into steam, and that the steam could push a piston up and down. It was originally designed to pull water out of coal mines. Okay? And so, interestingly, you used coal to heat up the water. This would then create the steam, push the piston up, create a vacuum, pull the piston down. Okay? Revolutionary. It really, for the first time, allowed people to move beyond the limits of their own strength, physical strength, or the strength of animals. Right? This is now leveraging what may seem obvious to many of us now, the transformation of potential energy to kinetic energy. Now, one interesting thing, though, is that many of you probably have not heard of Thomas Newcomen. You probably have heard of James Watt. He didn't invent the steam engine. He made it much more efficient. Right? And so I think that's a good lesson for us all as well, that efficiency and performance can be and is transformative. So his key ideas. He separated the cooling from the heating in two separate canisters. And this meant that once you create the steam, you didn't have to actually heat it all the way back up to create the vacuum again. He also introduced this gearing system, right, that basically it was focused initially on pumping water in and out of coal mines, but it also created the ability to spin a wheel with incredible power. And this then actually revolutionized history. So what he did was essentially make steam power 5 times more efficient. And you see the highlight here, right around 1760. Initial invention, 1712 or so, had 1% efficiency. His invention, 5x'd it, 4x'd it. This continued for hundreds of years, but this was the tipping point, this 5x efficiency improvement. It didn't just change how we made fabric. Right? It, in the end, wound up rewriting civilization. If you think about what the world was like in the 1600s, and then think about what the world became like by the end of the 1700s and into the 1800s, radical transformation across all of society. Right? It connected continents. Right? It allowed steamships, railroads, trains to travel long distances. Again, moving beyond the limits of human or animal strength. Right? Transforming potential energy to kinetic energy. That would continue into the second industrial revolution. It invented the factory. It essentially built the city. And it laid the entire foundation for the modern world. So now, if I were to ask you, looking back 300 years or so, was the Industrial Revolution a good thing? Are you glad that it happened? I'm guessing many of you would say, oh yeah, absolutely. I can't imagine life without the pinnings of the Industrial Revolution. But I'll also encourage us to reflect that the Industrial Revolution was incredibly disruptive and painful. Right? For many, many, many people, most people, actually, where it was happening. I mean, I'll highlight a horrifying statistic. Industrial Revolution was centered in England, in Manchester, right around 1780, Manchester, England. The average age of male was 13. That's how long they lived. That's how disruptive the Industrial Revolution was. So these as a society, as we think through these massive revolutions, we also have to think about the responsibility that goes along with it. We can think about what it looks like at the other end with optimism, and we should, but we also must look at where we are and how we get there in a responsible manner. Okay, so now let's look also at a really interesting phenomenon that took place during this exact moment with James Watt. An economist named Jevons coined a term, Jevons paradox is known as, that this massive increase in efficiency, 5 times increase in efficiency, actually led to a massive increase in demand for coal. You would think 5 times more efficient, you'd need less coal. The exact opposite happened. Coal spiked, right? Why? The innovation led to a cost reduction. But this key here is that with the cost reduction, we now had entirely new use cases that were never imagined before. And it was that spinning wheel that actually enabled it. Right? It wasn't now just restricted to pumping water out of a coal mine. It enabled the factory. It enabled many, many use cases that weren't possible before. It allowed basically things to move away. The equivalent of this would have had to be close to a water source. Now you could centralize factories in cities, et cetera. And this induced new demand, drove the need through economic pressure for even more innovation. Right? And so as these innovations took place, we now had more and more uses for this new technology. As you drive the innovation, as you drive the efficiency, people use it in more interesting ways. Okay, so this shows the fallacy of finite work. 1,000x efficiency doesn't mean 1/1000th the workforce. Right? In other words, the reality is human ambition knows no bounds. Now you could say, hey, we can, with 1/1000th people, make the same amount of cloth we made before, or harvest the same number of fields. That's not what humanity decided. They decided that they were going to go 1,000,000x, not just take advantage of that deficiency. So I believe we're in the process of going through that same transformation here. Lowering the cost of a fundamental resource, whether it's power or intelligence, exponentially increases its consumption. Right? Opens up all new use cases that you might never have imagined before. We don't automate the present. What we do is we unlock the previously impossible. Watt could not have imagined what his invention would be used for. Right? In the internal combustion engine, which through 100 years plus of invention came after his, couldn't have been something that he predicted. Right? So what it does, though, is it unlocks the previously impossible. There is this messy middle, and I really don't want to ignore that. Right? It's the turbulence of these economic phase transitions and the structural realignment that we all have to go through to make it happen. Really, really challenging, and what I want to do is actually, as technologists, have us take responsibility for managing this as well. Okay, so the Industrial Revolution, muscle multiplier, moved beyond the limits of what physical strength, whether of humans or animals, could accomplish. I believe that this era of intelligence is the mind multiplier. It's going to move beyond what any individual can do. And what I'll also encourage you to think about is there a shortage of intelligence in the world today? Do we have enough doctors? Do we have enough teachers? Right? Go down the list. I say no, actually. Right? In other words, if you think about health, if you think about education, if you think about science, are we moving fast enough? Are we able to educate and heal all the people that we need to? Absolutely not. There's a shortage of intelligence, actually. So something that multiplies our capabilities, it will be, in the end, incredibly powerful for society. And we're going to invent many, many use cases and capabilities that we didn't even imagine before. Okay, so what this means today, we're seeing the glimpses. AlphaFold is one of my favorites. Right? It solved a 50-year-old protein folding problem. 200 million proteins, basically perfect structure, unprecedented accuracy. What would have taken many years for each of these individual 200 million proteins can now be done in hours or even minutes. Right? One of the fastest to actually go from idea to Nobel Prize ever. Right? And because people could see exactly how meaningful this has been. And this has led to breakthrough after breakthrough after breakthrough, from experimental, empirical, to the theoretical, to the computational. So this will be absolutely transformative for science. Again, I'll ask, are we moving fast enough with our advancements? Do you wish that you could move faster with your advancements? And I think the answer is yes, you do wish that you could go faster. These technologies will enable it. We're developing things like AI co-scientists that actually allow us to not just do protein folding, but evaluate hypotheses in arenas such that communities of thought coming together in different ways can select the best approaches. Again, things that might take years of publication and then follow-on publication and follow-on publication can now be condensed into months, perhaps, or weeks. So for this community in particular, again, most exciting time, because the path to this intelligence isn't just about bigger models. Those help for sure. But it's about the radical re-architecture of the entire computer stack. So we get to invent exactly what computing is going to look like, starting now. Looking back, this community, the network systems community, the work it's done over 25 years or so, it's been transformative. Right? Like, in other words, if you think back as to what life was like roughly in the late 90s, it is more or less unrecognizable in many good ways and some bad ways relative to that time period. Right? It's been transformative for how we live, how we work, how we play across the entire planet. Interestingly, it's also the work that we've done. It's also laid the groundwork for efficient scale-out compute. Right? Data centers, networks that scaled out to tens of thousands, hundreds of thousands of elements in parallel, that in turn provide digital access to the totality of human knowledge. This AI moment wouldn't have been possible if you think about it purely in terms of the network systems community, NSDI. What this community, of course with others, has enabled is scale-out compute at just unbelievable power that has brought data to bear on any problem. So ML would not be possible without these scale-out underpinnings, and of course without access to all this data in digital form. So we've enabled this moment. Now we get to see it through. Importantly, the demand for compute has never been bigger. Right? Just absolutely enormous. I've never seen anything like this. We've seen doubling in demand every 18 months, let's say 24 months. But here in ML compute, whether you count the number of parameters for the largest models and then the amount of compute that they're consuming, it's literally 10x a year. Right? So the amount of compute that we need to deliver to support the growth on the curves that we're on is growing at an unbelievable rate. Now, unfortunately, improvements in the models and the capabilities of the models is much less than linear. Much, much, much less than linear. But still, they're there and they're meaningful, and it's those corner cases, those increasingly hard cases that we have to go after. So improvements are going to come on many, many different fronts. And so this is actually one of my favorite graphs from the last, let's say, 10 years or so. Famous paper, Scaling Laws for Neural Language Models. And what this shows is test loss on the y-axis as a function of the number of parameters on the x-axis. So as many of you are familiar, lower test loss is better, higher quality model. You want lower test loss. It takes more parameters and hence more compute to deliver that. Now, what this paper was showing is that actually the more compute you can throw at a problem, the better the resulting model is going to be. But it also shows something really, really interesting, which is the transition from LSTMs, or long short-term memory, which was the dominant algorithm for these models, let's say pre-2017, and then transformers, what's happened since. And if you look at these curves, the takeaway will be really, really incredible, a 5x efficiency improvement in terms of compute for test loss in going from LSTMs, the previous state-of-the-art, to transformers. Massive breakthrough. So now you could get the same test loss with 5x less compute, or move further down the curve and get a better model. This algorithmic efficiency continues. There hasn't been a breakthrough of the order of transformers yet, but I believe there will be, by the way. And if you look at the curve for steam power efficiency over hundreds of years, I think that's going to get compressed. But it was that breakthrough, right, that 5x, that allowed Watt's invention to really drive massive change. I think transformers, very, very similar. More is coming. But with transformers, the previously impossible now becomes possible, driving a massive, massive increase in the demand for compute. We didn't just say, hey, things are 5x less efficient, let's go buy 5 times fewer computers. We said, oh my gosh, we have to 10x it, 100x it, 1000x it. So another paper that I really like from the last few years, this is more of an essay from Rich Seddon, a Turing Award winner, and it's called The Bitter Lesson. I'll read the beginning of it to you. The biggest lesson can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by a large margin. And basically, throw raw compute at the problem, and you'll be able to make progress on AI. And if you read through the whole paper, what he says is, and it's been bitter for the AI community, because if you try to encode your cleverness into the algorithm, you'll probably get a one-time bump, but your encoding your cleverness, think of an expert system, is going to be brittle. Throwing more compute at whether it's reinforcement learning or these hidden metric spaces is the ultimate winner. And so one of, perhaps the key enabler for progress in AI and for AI researchers is more and more efficient compute. And by the way, all this compute is networked. OK, so we're moving from the age of information to the era of intelligence. I had the privilege at my SIGCOMM keynote in 2020 to talk about the 5 epochs of distributed systems that we were going through, and that we were in the beginnings of this 5th epoch. We had delivered 2x scale and efficiency every 2 years for 1,000x improvements over a 20-year period. Today, it's very clear that we're in this 5th epoch, maybe about the middle of it. We'll know looking back in a few years. But the needs are just radically higher. The need for innovation is radically higher. Today, at the very least, we have to deliver 4x the scale and efficiency every year. Right? Every year for delivering that same 1,000x that we delivered in 20 years, every 5 years. And just at the moment, when actually all the techniques that we developed in the last epoch, the last 25 years, no longer apply. So what are we going to do across hardware, across networking, across distributed systems to fulfill the needs of the larger community? OK, and so then this leads to the architecture of intelligence. We go through the hardware foundation, the network is the nervous system, and then, of course, the orchestrator, which is the distributed system that's going to put it all together. I am going to take a Google-centric view here because that's what I know best. But I believe that the ideas here actually are broadly applicable, and they're not unique to Google. So I think there are lessons that can be taken for, of course, industry, but also from academia in how we do our work to make advances across all three to push the state of the art forward. OK, so start with the hardware foundation. And really, what we're seeing now is this second wave of hardware specialization. In the history of computing, traditional wisdom, conventional wisdom has been you don't build a specialized compute engine. A CPU is always going to win, right? Because in the past, Moore's law, double in performance every 18 to 24 months. Just wait a while, and things will get faster and better. You can't keep up with a specialized architecture. Interestingly, over the past 20 to 25 years, there have been a couple of exceptions. One that I'll highlight is actually the heart of this community, a network switch. Right? It's a highly, you could do network switching on a CPU. No reason why you cannot. Famous papers have been written on how you would use an array of CPUs to do network switching, in fact. And hosts do a version of network switching, but the heart of the internet and the heart of every data center are these highly specialized pieces of silicon that are incredibly good at data movement. with very specialized computation. If you think about it, I decrement the TTL, I recalculate a CRC, maybe I encapsulate the packet inside another packet header, or I modify the destination address. But it is very, very specialized. CPUs are not good at this. If you take the problem and you say, hey, I'm going to only move data in this manner, and I'm going to have this very restricted computation on it, a switch will be 100x or more efficient than a CPU. It's not to say a CPU can't do it, it's not economical. So some really interesting specialized hardware was developed for this. And amazingly, data center networks exploded. The internet exploded. Why? Because now it became possible for me to create multi-layer fat trees that can connect 100,000 CPUs together, non-blocking, because of this breakthrough in efficiency of the switches and merchant silicon. We're seeing that exact same moment with AI at even a larger scale of demand. Right? So if you think about it, an AI computation, whether training, whether inference, is really about high-speed data movement, but with even more computation. If you look at modern models today, actually, data movement might dominate relative to computation. So it is orchestrated across thousands, tens of thousands, perhaps, hundreds of thousands of individual elements, massively high speed, nanosecond scale data movement with significant and different matrix algebra operations thrown in. This specialization was required because, again, if you try to do this on CPUs, it would be at least 100x, if not 1,000x less efficient. It's not that CPUs can't do them, it's that they can't do them efficiently enough. And the demand for this kind of compute is absolutely exploding. So we at Google saw this, the effort actually kicked off to build tensor processing units, specialized compute for carrying out these matrix operations. Initially, back then, it could fit on a single chip. That was TPU v1. It launched in 2015. From there, though, we realized that single chip inference was only a small portion of the workloads. And we realized that actually training these models could run across these same matrix algebra operations. But now you needed to network things together at really high speed. And I remember when we kicked off TPU v2, which was going to connect 256 of these TPUs together at really, really high speed and super low latency, we made the decision that it would not be connected via Ethernet. This was, for someone like me, who'd been working in networking for many, many years, shocking. Like, if you're going to do a network, it's going to be Ethernet. That was the conventional wisdom. A specialized network that didn't run IP was, on its face, a bad idea. I was wrong. I was really, really wrong. Why? Because it was even a more specialized use case. It wasn't about packets being forwarded across the internet. It was about essentially a distributed shared memory system. We could talk about that as well. The conventional wisdom from the past 20 years, lots of OSDI and SOSP and NSDI papers, was distributed shared memory, especially with hardware support, not a good idea. For this domain, it turned out to be necessary. Right? And so this was great foresight. Then from there, generation after generation, we moved to liquid cooling. Again, something that was considered not a good idea for data centers, but to deliver the highest levels of efficiency, both in raw performance, but also in density, turned out to be a requirement. Generation after generation, we iterated, right? And wound up actually with the most recent announcements of TPU v8. So the 8th generation was just announced a couple of weeks ago. 8T for training and 8I for inference. Last interesting observation for me here is that we're now seeing even more specialization. So we now have 2 chips because the needs of the 2 workloads have diverged sufficiently where we need to specialize even further, right? The T chip for training, the I chip for inference. Lesson here for me, and I think for the community, is it is the need for specialization, while counter to maybe the conventional wisdom that we developed earlier, is only going to increase. And the more you specialize the hardware, the more efficient it will be relative to its more general purpose counterpart. So if you can find a workload big enough, and that's key, you wouldn't build specialized hardware for 0.01% of your workload. Even if it were 10x or 100x faster, you'd still go put it on the more general hardware. But if it's a big enough workload, specializing matters. And for both training and inference, they're big enough workloads where specializing really makes a big difference and a big benefit. OK, so taken together, whether it's specialized silicon features, high bandwidth interconnect, this ICI, inter-chip interconnect topologies, scaling across the entire data center, novel techniques, including liquid cooling and vertical power delivery, to really drive the efficiency of the hardware. At least, and I want to be conservative here, 100x system efficiency that you get in perf, in power, and in cost. But now, interestingly, and this was early on, we're on a curve right now where we're increasing all these measures by close to a factor of 2 every year, at a time when general purpose CPUs are improving in performance, normalized to cost, about 5% a year. Right? So the baseline of 100x, enormous, but they're wildly different curves. Right? Rate of improvement of general purpose compute at this point, very slow. Rate of improvement that we're still able to drive with the specialized compute, really, really on the specialized, on the high-end curve for the specialized compute. OK, so now what's going to tie this all together, though? So each of these pieces of hardware are really, really interesting, the chips. But it's the network that is really the nervous system that puts it all together. And so what I'd like to convey here is that the network is a fractal, actually. And that while the domain of this community is fantastic, I would actually encourage you all to be even thinking at further extremes. I see some signs of it. But there is really, really interesting networks on a chip. And in fact, the network on a chip may dominate the capabilities of the chips, probably understudied by the community as a whole, and especially the research community. Rack scale, there's been some nice work, I think, in this community and others. But probably more is needed there because we're able to drive much higher levels of integration into a rack. Historically, a rack might have been 30 kilowatts. In a few years, people are aiming for 500 kilowatts, a megawatt per rack. So the amount of compute, the raw amount of compute that you could put into a rack really changes. And the network, of course, that pulls it all together is really going to have to change as well. Cluster scale, I don't need to say a lot about, you all know a lot about cluster scale. Planet scale, WAN, continues to be super important. But interestingly, moving into space, if we're thinking in terms of research, and we should be with a 5-year horizon, a 10-year horizon, is going to be interesting. I'm not quite sure, but it may even be inevitable. Right? The jury's still out, but really, really interesting work to be done there. OK, so let me start with, the fractal nature of the networking at these different scales. Let's start with the nanometer scale, the chip. This is from public material of a TPU. Right? What's inside a TPU? Many different elements. I don't know if everybody can see them, but in the sort of light blue, we have the matrix multiply units and the vector units as well. Lots of computes. But if you look at it there, and actually if you look at the chip real estate, a huge amount of it is dedicated to memory and direct memory access to high bandwidth memory, HBM. So many of the things that we might be accustomed to in terms of CPU to memory access apply directly here. And the pipeline of getting data off of memory and onto the chip, especially with respect to what's labeled VMEM here. Think of it as specialized SRAM for the ML chip case. The residency, how you manage that data, how you manage the KV cache, how you shuttle things in and out, absolutely critical to the performance of these chips. Now, increasingly, what you can see here is we're entering the age of a version of multi-core, but multi-die. So there are 2 entire compute chips, what would have previously been chips, in a single package. Right? You see the 2 copies right next to one another. There's something called die-to-die, right? A high-speed interconnect between these 2 chips on a package that allows for communication between the 2 of them. Right? It's another layer in the memory hierarchy, essentially. It's a really fast one, but it's not quite as fast as what's on each of the individual chips. Managing that is also something that this community knows a lot about. And then, of course, for these chips, the network is on the chip. So ICI, the inter-chip interconnect, that winds up connecting these TPUs, in our case, together in a torus topology, but not just, as we'll see in a moment. Does routing, does forwarding at massive speeds on the chip. So not quite the speed of a high-end Ethernet switch, but not far away of the total speed, bisection bandwidth of a high-end Ethernet switch is right on the same chip. So managing that, essentially communication, but also computation. So for example, there's this small box that you probably can't see. It's labeled SCCAE. It's a collectives acceleration engine. It's basically very specialized compute that is on the router designed to make the collectives go faster. Right? So think of it as the simpler math that can take place on parameter distribution to make some of the calculations right next to the router to forward things at ultra-low latency across tens of thousands of chips or more. Designing things like this, massive benefits. Why? Because I don't have to then move the data all the way to the compute engines. If I don't need the full-on matrix multiplication at the largest scale, if I can take care of things right next to the router switch, things go much faster. A way to think about this is the limiter in all these chips is power. And the number one consumer of power on any chip is data movement. So thinking in terms of locality of computes, putting the data right next to the compute as much as possible, super interesting. And now, it bends my mind, hopefully it'll bend yours a little bit, think in terms of 3D stacking. Now imagine that we can put a SRAM layer on top of the compute layer, not next to, but on top. Now that you have 3 dimensions for locality, you can imagine actually putting the right data on top of the right compute, minimizing the amount of movement for those bits, making the entire chip much more efficient. What I really want to convey here is actually we're in early days. It's going to be really hard. It's not going to happen overnight. But the space of optimization on chip, just massive. Right, so in other words, these 2x's are out there. Right? Not in a 10-year period or a 20-year period, but in an annual period. Also on chip, on our NIC side, we're building Falcon, and actually through nice work on the standards committees as well. And for this one, it is another instance of specialization, one where we've been able to leverage our experience to, I believe, finally put in scalable, robust, meaning reliable, transport for a range of upper layer protocols, storage, RDMA, and more, on a common engine, while giving solutions in hardware to some of the age-old problems like incast, like congestion collapse, et cetera. And to make this available to every server to coordinate with, whether it's TPUs or GPUs or your favorite XPU as well. Lots of innovation to be done on the silicon side here, also on thinking through how you would make this just programmable enough. Right? In other words, the more specialized you make it, the faster it'll be. The more programmable you make it, the more robust and extensible it'll be. And so finding that balance point, lots of really interesting opportunities there as well. OK, so now moving to the rack scale. One of the things that we found with our inference solution, TPU-8i, is that actually latency is the key benefit for emerging workloads, including reinforcement learning, but also just serving, because existing chips and systems are built for throughput. They deliver massive performance, but you have to have a big batch size. What that means is, like, if I can put many inference requests, 100 or 1,000 through at the same time, I'll get great utilization of my chip and system. If I put one in at a time, I'm not going to get great utilization, and the latency, because of the deep pipelines that I have, is not going to be as strong as I'd want it to be. So around this, with TPU-8i, we had a number of innovations, including that collectives acceleration engine. But another one that, again, this community will really appreciate was a new topology that was designed to minimize the number of hops, maximum number of hops across the network. So rather than build a torus with connectivity to all your neighbors, we essentially took a variant of a dragonfly topology, where each chip was direct connected to multiple chips on a board and within a rack. And then the racks were connected to one another in a torus topology. Relatively simple idea. Took a while to make happen and took a while to make work, but relatively simple idea, half the latency of the system. And in a world where latency matters, half the latency actually means twice the efficiency, right? If you really care about how quickly each result comes back, this is a massive win. And I'm certain there's actually more that can happen here as well. OK, so a key thing here is reliability across all these systems. So I mentioned that these racks with the board fly, for example, and TPU 8i are connected to one another to form. So we have a 1,152 chip topology. This means that with 8i, you can basically serve the largest models. You shard them, partition them across all the chips. Some subset of them, you probably are going to co-schedule multiple models across subsets of the chips. The key here, though, is that the failure of any individual TPU means that actually an entire model could go away. Why? Because if I have a model running across 256 chips, say, one of the chips fails, I now have a topology that I've essentially hard-coded for the distribution of parameters and state across them. One of them fails, and now I have to reconfigure. The way we manage that reconfiguration, and a key breakthrough for us in the TPU world, has been in leveraging optical circuit switches. And so the idea here is that essentially by having a, let's say, single standby rack, if there is a TPU failure, what we can do is we can very quickly reconfigure the entire topology to remove the bad rack and put in a new one with the exact same logical topology that the application had before. And so how this works is, essentially, we connect all the fiber coming out of the racks through a series of optical circuit switches, and that's depicted here. Each optical circuit switch has two of these chips. This is actually one of our Google optical circuit switches. You can't see them here, but each one of these chips has 136 MEMS-controlled mirrors, tiny mirrors. You see 3 of them on each of the chips here. You can rotate them in 3 dimensions. And essentially, with the fiber coming into an optical circuit switch, you shine in open space. The light bounces off a mirror, hits that mirror, gets reflected at the right orientation to go to another mirror that then reflects the light back out an output port. So by rotating these mirrors appropriately, you can create an n-by-n crossbar and reconfigure topologies by essentially moving fibers without moving fibers. You create these patch panels that will allow, just like the old-style telephone networks, would allow you to create circuits by creating a jumper cable. This is the equivalent of that jumper in free space optics. This has been a game changer for us in terms of reliability, right, and deployments, which means that the throughput, the utilization of our chips has gone way up relative to earlier systems. Okay, so AT, really focused on scale, goes to 9,600 TPUs, also has the same OCS connecting it at even larger scale. And it really is about this shared high bandwidth memory, 2 petabytes across the 9,600 chips. That allows you to go at massive scale, connecting all these chips coordinated at nanosecond granularity. Okay, and I won't go through the details here, but essentially it is this 3-dimensional torus with the rack as the building block. From there, 9,600 winds up being great, but not quite enough for the scale that we want to operate. So we're seeing that these models are consuming increasingly tens of thousands, perhaps hundreds of thousands of chips. So what we then need to do is connect the individual, what we call pods, of 9,600 TPUs together via a data center network at even larger scale. So we've been working on our Jupyter fabrics over, it's been 10 plus years now, 15 years or so, scaling it from a petabit to 6 petabits to 12 petabits, and now the most recent Virgo fabric that we're actually launching goes to 47 petabits per second of non-blocking bandwidth, designed to connect these TPUs at the largest scale. What this means is that we can have 134,000 TPUs, actually, across many pods that can be connected together with non-blocking bandwidth at the Ethernet level. So the Ethernet is basically another layer in the hierarchy relative to the ICI. Leveraging jacks and pathways are software systems. This scales all the way out to 1 million TPUs. And that allows us to actually scale further across the WAN. So If you start doing the math in terms of how much power 134,000 TPUs consumes or 1 million TPUs consumes, same math applies to GPUs as well. You actually either cannot or do not want to put all of that compute into one building. You can't. 2 buildings in the same place, 10 buildings in the same place. You need to scale out across the wide area. And hence, you need something like before Google's software-defined WAN to connect all these different regions together and be able to carry out the computation synchronously across the wide area network, bringing together some of the same fault tolerance techniques. Now, a WAN network has its own challenges in terms of scaling out rapidly and in managing failures incredibly rapidly. So many of the same issues with traffic engineering, SLOs, reliability, et cetera, continue to apply. But the rate of growth actually, in other words, we've seen massive growth in our WAN, before WAN in particular. It's gone on yet another exponential with AI. So managing all that while growing the demand for bandwidth between the sites has been really, really interesting as well. OK, and so we talked about chip scale. We talked about rack scale networking. We talked about cluster scale networking, of course, the wide area network. Lots and lots of interesting and new, both existing problems and new problems that come up. I also want to spend a second forward-looking talking about extraterrestrial, moving beyond the planet. So what is the motivator here? In the end, if you are able to put compute in space on a sun-synchronous orbit, you can have 24/7 renewable power with 5x or more the efficiency of what, let's say, solar power on the Earth would be, just from atmosphere and distance and everything else. Many, many challenges here, many challenges. So this, I am not at all suggesting this is a solved problem or it's going to solve the energy problem in the short term. But as a research direction, incredibly exciting. And now if you think about some of the particular challenges of space in terms of launch payloads, how big something can be launched, it won't be big enough to handle the largest computation that we'd want. So how do you coordinate from a networking perspective once you are in space? Maybe you have 10 modules, 100 modules, 1,000 modules. How do they talk to one another? Right? Maybe each module looks roughly like a rack. Now, even the hardware probably looks very different. It's not going to look like a rack. In space, the optimization points are going to be very different. But there will be many, many networking challenges, actually, that go along with it, power challenges that go along with it as well. Thinking through those and making it possible to leverage this capability over some number of years, exciting domain for research as well. OK, I want to leave time for questions. So I'm actually going to skip much of the last bit, which is one of the most important bits as well, which is about the software control for all of these large-scale networks and hardware, TPUs, GPUs, or otherwise. What I will skip to is actually this view, which is everything that I told you about to some extent was about theoretical performance. Not theoretical performance in that the performance numbers I told you are real. They're in the hardware, for sure. But they're benchmark-based. What I mean is what we always do, and that everybody does, is we say, if I run my benchmark on a hardware configuration under perfect conditions, this is the performance that it's going to deliver relative to the last generation, which was also run on perfect conditions. The reality is perfect conditions don't exist. Right? So very quickly, and we talked about the failure issue, and we talked about the benefits that OCS gave you. Think of that as one of 1,000 issues that hit you in production when you're trying to run a job. If you've ever tried to run a job on, let's say, 64 GPUs or 64 TPUs, you've probably had to fight failure. You've had to fight actually getting performance out of the system. Now imagine taking that out to 64,000 or 256,000. Right? Just from simple statistics, you're going to get hit with issues all the time. If you're running a synchronous computation, your good put, your productivity, is going to plummet. In other words, there's a theoretical performance that you could deliver if everything's going well. That never happens. So what fraction of that perfect performance can you achieve on your real hardware, on your real network, on your real system, also in a multi-programmed environment? Right? And it's not that you're always running. I mean, the one hero job you can look at. But in reality, you're probably running thousands, tens of thousands of jobs. They're coming, they're going. There's holes created by one that need to be occupied by another. So you've got this, not surprising to anyone here at this point, multi-billion-dollar infrastructure that in theory can deliver some amount of performance. The key question, though, is what's the good put that you can deliver in practice? Right? If 100% is theoretical perfection, what can you get to under realistic conditions? And naively, baseline could easily be 25%, 30%, 40%, perhaps even lower. It takes enormous amount of work, telemetry, by the way, so across all the standard things that you think about, mean time to detection, mean time to repair, right? And more, all come into play in managing this incredibly large-scale system in a very dynamic environment. So from a software perspective, an orchestration perspective, and we have a system called Borg that manages this, what developers and researchers want is an abstraction of a job queue. They submit their job. That job has dependencies, by the way, CPU, data, network, and ML. It gets run wherever it's best, delivering the maximum. And then as the person who owns the infrastructure, you want to run all those jobs as well as possible while minimizing your investment or maximizing the capabilities that you get out. So thinking through the software complexity, the end system that wraps all this together, and how it runs well, key challenge. So you can make things more efficient with better algorithms, LSTM to transformers, and transformers to many things that come next. You can make things more efficient with better hardware. One of the biggest, maybe the biggest of them all still, is the software orchestration around it all, actually. And so I don't want us to lose sight of that. Hardware is great, algorithm's great, but the network and the distributed system that connects it all together, equally great. Okay, so let's talk about some of the things that come next, and then I'd be happy if people are interested to take a few questions as well. Okay, so we're now at this transition point to agents. I think many of you are familiar with this, right? Training, inference, but then agents. So how do we think about this at scale? One aspect is sovereign infrastructure. Many want to make sure that they own their data and their infrastructure. How do you manage the security? How do you manage the reliability, like we've been talking about, and really the societal impact of distributing this infrastructure across the planet? The agentic computing I want to talk about because it really involves the swarm of agents working together and leveraging tools, meaning software, that communicate at massive scale. So what I want us to be thinking about is, if I have these agents, they might actually be building software, writing software, quote unquote, building it, testing it, executing it, taking the output, inserting it as context into another inference run, and doing this in as tight a loop as possible. So really, it is this composition of, there's going to be return of excitement over CPUs. When I said TPUs are needed, let's say GPUs are needed, of course, and they're rising in popularity. But CPUs didn't go away, they won't go away, and I think over the next few years, we're going to see a return to the future where managing the computation of these agents, right, taking the right input, the right output, composing them as context for your inference runs in a very efficient, tight loop is going to be critical. One of the big challenges today, actually, with agents is that these TPUs and GPUs sit idle while waiting for the CPUs to do their work. Right? That's almost a sin. So how do we actually make sure that pipeline across data, network, compute, accelerator works perfectly, or much more perfectly than it does today? Power, medium to long term, this could well be our biggest challenge. And so power efficient network systems, and you saw the fractal nature from chip to extraterrestrial, all critical. And what we're thinking about at Google is moving all our thinking to not performance efficiency, but performance per provisioned watt. So this is not theoretical. This is not saying if I had a perfectly sized system and perfect power delivery, what is my performance. It's actually saying when I put my chips into my data center with some amount of power at the edge, how much performance do I get for that provisioned power? If I provision a huge amount of power and only use a fraction of it, I can't feel good about it, even if I deliver really great performance, because I've wasted, to some extent, my most precious commodity, power. Similarly, performance per emissions as a key metric for us to measure and optimize. I do want to come back to this messy middle. We are in the early stages of significant societal transformation, and our role as technologists, I believe, is more important than ever. So there is going to be some turbulence. There is going to be some stress. What can we do from the technical side, and also from an influence side, to ensure that this technology is brought to the world in the most responsible, least disruptive, and of course, most uplifting way possible? In other words, I'm an optimistic person by nature. What I think about is a teacher for every student, a doctor for every patient, and a cure for every disease. That's what I think about. That's what drives me. But we also have to go in with eyes wide open with respect to what the costs will be to getting there. What do we do from the technology side to manage that? OK, so I'll stop here, maybe leave a few minutes for questions, depending on how long Shrikant and Kim want. So what we went through here was some of the history, what this means for today for us in AI, and then in particular for this community, what the architecture of intelligence looks like. I hope that you see across hardware, networking, and orchestration, what the architecture of intelligence needs is center to this community. And of course, many, many things that are going to come in the coming years that are going to be really exciting for this community as well. OK, thank you very much.